In this short video on ADS momentum, I'll cover a quick overview, including the steps for using momentum. Then I'll show you a setup and layout to demonstrate how momentum works and its value, and that will be seen when we look at the results in the data display. Finally, a built-in example of a spiral inductor. This list gives an overview of ADS momentum. It describes what it is and what it can do for you. So basically, it's an electromagnetic solver. It runs out of ADS layout, and you can get S parameter results, so you can have a model for any passive structure that you can draw and lay out and set up correctly with momentum. It does use, as you can see here in this list, method of moments. It solves passive structures that are three-dimensional with some restrictions. It does vias easily. It uses pre-computed Green's functions, so it can go quickly if you have everything done in advance. A mesh pattern or grid of cells is set up over each structure, and you'll see that. We call it a mesh, and then each cell is solved with relationship to all the other cells, both in the X and Y direction. So it can do coupling extremely well. You can visualize current, look at far-field patterns. You can create look-alike components, and basically this means that if you draw, for example, a spiral inductor and solve it in momentum, you can then have that drawing put back in schematic, and it looks exactly like the spiral you drew. So it's basically a symbol for your momentum solved spiral inductor or anything else you draw. And we can do co-simulation. Now, we're not going to focus on some of these details. We're going to cover the basics of using momentum. So let's look at the steps next that you'd take to do a momentum simulation. And here are the basic steps for using ADS momentum. Now, I want to point out that we have a momentum course that covers all the details, all the different types of structures, substrates, vias, 3D, coplanar waveguide. That's all covered in the momentum course. But for this video, we'll use a very simple example. Now, you can start in schematic in ADS, and if you do, all the components require footprints or artwork, and that's automatically generated into ADS layout. So beginning in ADS layout, and you can even import files from other drawing formats, you make sure that you have ports connected to your structure, and then you define the layers. And the layers include both the substrate material, where we define that material, and you can have multiple layers, and then the mapping of all the individual drawing layers to the substrate layers. Once that's done, the momentum engine will then create the mesh pattern. That's what you see here. A series of individual cells or grid pattern where all the L, R, and C values of each one of these is calculated with respect to all the other cells in both the X and the Y direction. And that includes coupling that could exist between closely spaced lines. And the result, after the analysis is run, is an S parameter model for your passive layout. Now, let me show you how this is actually done in ADS. I'm beginning in schematic, and I'll create the layout from this schematic design. I've taken elements from the microstrip palette. These include microstrip lines or emblans and microstrip corners. There are two ports grounded here for the S parameter simulation, so we'll get the results of this. Now, creating the layout is simple because the command layout generate update layout automatically creates the layout, and that's because we're using artwork generated from ADS with these microstrip lines. And here's the result. As you can see, we have the S meander line, and the width and the spacing is the same. So I want to go back to schematic for a moment and show you how I set this up, and then we'll look at the results that the circuit simulator gives for this design. To create the spacing, this emblem and this emblem use a variable for the length, as you can see here, L equals S mils, and then I simply set the variable here, S equals 10. And that results in 10 mils here and 10 mils here for our spacing. X10 is the width, and you can see X mils, and that's for the entire meander line. So by having this set to a variable, I can go back and change the spacing easily, and that's how we'll see the value of momentum for this design, where there can be coupling between closely spaced lines. Now I'm going to run the simulation and plot the results. And here in the data display, I've plotted the results in a rectangular plot, dB of S21. So this is the transmission measurement through our S line. And you can see there's 1 dB or less of loss, and it varies across our frequency sweep from 1 to 10 gigahertz. Now, let's go back to layout and set up a momentum simulation and compare the results from the circuit simulator. So I'll be plotting both traces on the same plot, and we'll see if they match. So let's begin here in layout where you see the momentum command. If you click on it, the first menu choice is to enable the RF mode. If you have a circuit that's lower frequency, electrically small, then you want to use the RF mode. It's a little different solution process, but it works very fast. Because we have a higher frequency circuit, we won't enable that. So keep in mind this is just a toggle. And again, all of this is covered in our ADS momentum course. So the first thing we're going to do is set up our substrate. And to do that, we'll simply update it from schematic. And then we can look at it by going to this command, create modify. And here is the substrate menu. It shows both the substrate layers and the layout layers. And if you recall, our thickness was 5 mils. Here's the ER of 9.6, and that was simply transferred from schematic into momentum. And you can see the values here. And here in the Layout Layers tab, the drawing layer, which was conned, and they're all listed here, that microstrip drawing that we have is on this layer, and it's mapped, and the mapping is done down here, as a strip conductor, and it's between the interface of our dielectric material, that's the M sub, and free space. So just in review, although we copied from schematic, this is where you would set up your own substrate definitions. You could add, cut, and paste layers, define all their properties, give them a name, and then in the Layout Layers tab, you would then assign any drawing layers that are applicable, define their properties, and then map them as either strips, slots, or vias, depending upon what you're doing. So this is our substrate definition in momentum, the dielectric material and the drawing or layout layers. Now the next step will be to have our ports defined using this port editor, and I've already used this icon here to insert ports 1 and port 2. Here in the port editor you can select the port, and then it will allow you to define that type, internal, which would be if it was internal to the structure, or these other modes. We're going to use single mode, which happens to be the default, so you don't really have to set it. You can change the impedance as you see here. Let's cancel this, and let me zoom in and show you something important about ports for momentum. They need to be snapped to the edge of the metal to be calibrated, and that means at every frequency momentum will go back 1/2 wavelength so that you have 0 dB and 0 phase at this point, just like the calibrated ends of a network analyzer. Now before we set up the simulation, let me show you the mesh setup.